All right, science teacher friends. My name is Travis Laurent, and I'm a science teacher. And I just wanted to go through the new state standards for physical science for eighth grade. So the first class I actually taught back in 2006 was physical science for high school. I taught that for about 10 years. And now with us, the state of Minnesota making the switch where physical science is going to be taught in the eighth grade, I wanted to keep teaching physical science and physics type classes. So I'll be teaching in the middle school. So I thought it might be helpful since I've taught this before for me to go through the order and the new standards. And they're actually different than the high school standards, but there's a lot of overlap if you have taught physical science before. I'm going to point out just real quick at the top, this I just kind of sketched out, and sorry for the bad handwriting here, but this is kind of the order that we've decided to go in, and I've done it in different orders. So we're going to start with physics, then move to chemistry, and I kind of broke it up. We're going to go intro to motion and kind of intro to science and measurement, probably in here. I'm just using measurement tools. Force is Newton's laws of motion, and then momentum and energy. Even though the standards you'll see don't say the word momentum, it'll definitely make sense to tie in momentum with energy or momentum with forces. And then waves, you'll talk about just waves in general, then sound, and then waves in general with light. And then there'll be kind of a break, the way that our team decided to do it. And then we're going to the chemistry portion. So periodic table, elements, we'll talk about chemical reactions, phases of matter, and then engineering. And like I said, I've taught since 2006 now, and I've taught this class in different orders, and I could totally see. I actually think the way I learned it back in the day is we started here and then finished with physics. So I would say there's not a right order. I would say start with whichever way you feel more comfortable. I tend to consider myself more of a physics person, so I like starting with physics. And if you're more of a chemistry person, I could see start with chemistry first. So we're looking at the state standards, and just to point out the bottom, these are the Minnesota Academic Standards in Science. They say it's the final one, which if I was making this, I'd be like final, then final one. And anyway, but this is the final one, May 2022, and then edits were made. So this is the most recent one I could find. But we'll try to get this done in one video. Hopefully I don't have to roll into two, but we'll see how this goes. So if you're looking at this, there's the 7th grade. I crossed that one off because we're looking specifically at 8th grade. And then if you're printing out the standards, this is starting on page 50. I'm going to go ahead and ignore the grade since that's going to be the same. And then they give you the strand and the substrand and the standard because this doesn't really tell you specifically what you need to teach them. And I'm going to focus instead on the benchmark. So I know if I was at some kind of continuing education, this is where the presenter would say something like, now we're going to unpack the standards. I'm not going to say it. I'm just going to read the standard, and then I'm going to try to give you an example. And I guess technically that would be called unpacking, but I don't want to use that word. I just heard it too much. So let's look at this first one. It's under the matter and its interactions, but I'll read the benchmark here. It says, ask questions about locations of common elements on the periodic table to note patterns and properties of similarly grouped elements. So basically this is going, according to the way we're doing it, this will be going halfway through the year basically. So these standards that they're talking about are not written in like a coherent, and I don't mean that in a derogatory, but they're not written to like build on top of each other. So they're starting right away. We're going to go talking about the periodic table. So I just gave an example just to refresh. Maybe it's your first year teaching. Maybe you haven't taught chemistry in a while. Maybe you're being asked to teach physical science, and maybe you're a life science teacher, or maybe you're not used to teaching it. So the example I like is we have 2 protons here, 2 neutrons, 2 electrons. So basically what determines an element is what's in the atomic nucleus, and we have 2 protons, so that's helium. And what you can do is you can talk about changing the number of protons, and by changing the protons, that changes the element. So basically if you gave it another proton and had 3, then it'd be lithium, and every time you give it a proton in the nucleus, it becomes a different element. Changing the neutrons, remember, does not change this from helium. So if you change the neutrons by giving it a 3rd one, that would just change your atomic nucleus, how many neutrons are in there. That would change it, become a different isotope, right? So changing protons will change it to a different element. Changing neutrons changes it to a different isotope. And then if you affect the electrons, then you can turn it into a different ion. So if I were to take these 2 electrons away, right now it was neutral electrically, and you take the 2 electrons away, it's going to have a positive charge of +2. So that would actually be what's called an alpha particle. So basically it'd be 2 protons, 2 neutrons. So that's good old-fashioned chemistry. The next one is physics. So this one says, ask questions about data to determine the factors that affect the strength of electric and magnetic forces. And spoiler alert, the two factors are the amount of charge and the distance between charges. So the example that I have here, if I had a proton and a proton, so they're going to go ahead and they're going to repel. And if you change the amount of charge, and actually it would be the polarity of it. If you had a positive and a negative, remember, they'll go towards each other, and then negative, negative repel. So the two factors, amount of charge and distance, we kept these all the same distance. But if I wanted to make this even more strong repulsion, I could throw some more protons on there, and then the force of repulsion is going to be even greater. Now, what's commonly mistaken, or the kids make mistakes on, that's electric charges. The same two rules apply to magnetic poles. So you have a north pole of a magnet, of a bar magnet, and a north pole, and those are also going to repel. If you take the North Pole over here and the North Pole over here and they're further away, they're still going to repel, but they're going to repel less. So a point of common mistake is they'll call these charges over here for magnets. Magnets don't have charges, they have poles. So for magnets, you want to say opposite poles repel. For charges, you'd say, if they're the same pole, they repel. Over here, you'd say the same charges repel. Opposites attract. All right, so we got two out of the way. The next benchmark, it says plan and conduct an investigation of changes in pure substances when thermal energy is added or removed. So this is your classic picture where you have your three phases of matter. I'm not including the fourth phase, which would be plasma. So if you had a solid and you add energy to it, maybe by heating it, then remember your molecules are going to move even more. It will go to a liquid, and then this is becoming less dense. Add more energy to it, becomes a gas. More energy equals faster molecules. So particle motion, in this case, the molecules would be moving the fastest. That's not too bad. Being a physics teacher for many years, this is the one that people always have trouble with, and by people I mean students. It says, plan and conduct an investigation to provide evidence that the change in an object's motion depends on the sum of forces on the object and the mass of the object. So the example I like to give is, say you had a box on a table. And why this is frustrating to me just reading this is because this comes out of nowhere. This is actually Newton's second law, which says that F net, the net force on an object, is equal to its mass times acceleration. So if there's a net force acting on an object, that mass will accelerate. And accelerate means it's going to move. And it's going to change its velocity as it does so. So in this case, if you have just a box on a table, the force of gravity acts down. Another word for that would be the weight. The weight this object feels, that's a force due to gravity. And then there's a force of the table acting up that's equal but opposite in magnitude. And so another fancy word for this force from touching the table is called the normal force. And now these two forces are equal and opposite in direction. So those two vectors, and they don't say vectors anywhere in the standards, but you're going to have to introduce this. These two vectors are opposite in directions, so they'd cancel. So I'd say my net force on this object is 0, which means this is not going to accelerate. So if I want to make it move, maybe you give it a little push to the right. So maybe this is you, and you just go up to it and you push it. So I'm just going to say F push is 10 newtons. So if you have a net force, in this case, it's going to be a force of 10 newtons to the right. So I'll write that in red. F net is equal to 10 newtons, and we'll say to the right. So since there's no counterforce going the opposite way, that means we do have a net force in this case. And according to Newton's second law, which would make sense in my mind to do the first law on the standards first, but you have a net force acting on it, so that mass, that box, is going to accelerate, which means that this is going to start off going not very fast, and then each second that passes is going to go faster, faster, faster. Cool? So net forces will produce net accelerations. So that's Newton's second law. All right, the next benchmark, it says conduct an investigation, evaluate experimental design to provide evidence that fields exist between objects exerting forces on each other, even though they're not in contact. The easiest example I thought about for this one, I remember reading about Albert Einstein being mesmerized by a compass. But if you just have a bar magnet, North Pole, South Pole, and you have a compass, well, that compass itself is a little magnet, and you can see usually on that magnet, they'll label north and south on it, and you can see that it'll attract. So if you hold this compass next to that pole, it'll be attracted, and then if you bring it over to the other side, it's going to flip. So you can say conduct an investigation. Well, that's a pretty simple investigation. You just compass and a magnet, and that gets checked off pretty fast. Plan and conduct an investigation to determine how temperature of a substance is affected by the transfer of energy and amount of mass. The thing that I thought about back in the day we did is just heat different items, maybe different liquids, and measure the change in temperature, or maybe heat them all to a certain temperature and watch how the temperature changes throughout time. Cool. Or just heating up different objects. All right. Analyze and interpret data on the properties of the substance before and after the substances interact to determine if a chemical reaction has occurred. So this is your good old-fashioned chemical versus physical changes. So I know that you can probably Google this or get from a friend, but there's going to be some lab that is chemical versus physical change, where in the lab you're going to be burning stuff, or maybe you're mixing two reagents to make a new product, and maybe it forms like a precipitate. So you're going to have maybe some reactions that you burn or you're mixing to make a new product, and then you're going to have some probably where you're just heating or melting stuff, and you're just talking about during the physical change, it's the same substance but just in different forms. So molecularly it's the same substance. So that's your good old-fashioned chemical versus physical change lab. Construct and interpret graphical displays of data to describe the relationship of kinetic energy to the mass and the speed of the object. So what they're really telling you is you need to introduce them to this equation for kinetic energy. So kinetic energy is measured in joules. And then you're going to have mass measured in kilograms. And then V is velocity measured in meters per second. So I gave an example of two football players running at the same speed. So maybe their velocities are the same, but maybe you have a really massive football player. And a lot of times the way I'll illustrate something like that is if I do like KE, the big football player, I would do like 1/2, and I'd make the M really big, V squared. And then for the little football player, I'd do 1/2 M V squared. So you can see if you have more mass and you get hit by that football player, you're going to have a lot more energy. So that's why you see a big football player hit a little football player, a lot more kinetic energy from that big football player. But this standard benchmark is talking about this equation right there. Use mathematical representations to describe a simple model for waves that includes how the amplitude of a wave is related to the energy of a wave. Probably the easiest way to do this, you can download frequency samplers out there where you can whistle a note and you can whistle it really quiet, and you can see the amplitude of this wave is very low. And then if you whistle louder, you see, oh hey, it's taking them physically more energy. So then all of a sudden that translates into a larger amplitude of the sound wave. And then the one thing just to notice, the quiet sounds, the amplitude is lower. And the amplitude is measured from the midpoint of the wave to the crest of the wave. Sometimes it's confused. Students think you go from the crest of the wave to the trough, and that's not it. The amplitude of the wave goes from the crest of the wave to the midpoint, or you could say from the trough of the wave to the midpoint. Another example, you could talk about tsunami waves. Tsunami waves can be like 50 feet tall, and then obviously they do more damage when they hit shore versus like little waves, just normal ocean waves. So the damage would correspond to the energy of the wave. So sound waves probably the easiest. Yeah, and then tsunamis would be for water waves. Create a computer program to illustrate the transfer of energy within a system. I'll be honest, I would have to think about how to create a computer program, so that I just underline the word create. I will say that there's a pretty good simulator out there called PHET, P-H-E-T, I think it's lowercase t. But basically, I think there's a roller coaster one on there where they talk about, hey, if you're up here at the roller coaster at the top, you're all PE, so let's say there's 10 joules. There'd be way more than that because roller coasters are so heavy and so high, but you'd have zero kinetic energy, and then the point of emphasis would just be as you go down to their lowest point, 0 PE and then all KE. But notice when you add the PE and KE, it's equal to before and after because energy cannot be created or destroyed. So it always is going to sum to 10 joules. And then at the halfway point here, it's going to be 5 and 5.